One of the more complicated things is that when I'm talking about a reaction that's not at equilibrium, and can I predict the direction of change based off of this Q, this reaction quotient? All right, first let's define the reaction quotient. The reaction quotient is the ratio of the law of mass action, but when the reaction is not at equilibrium. In other words, it will only be equal to K, that constant value that we have experimentally determined or look up on a table or given, when it's at equilibrium. When it's not at equilibrium, I still can calculate this ratio, but it's going to be called Q instead of being called K. So the ratio Q is not constant. However, the value of Q compared to K will tell me something about where this direction is, what's going on with this reaction, how close is it to equilibrium. So the reaction quotient is used to determine which way the reaction will proceed to reach equilibrium. Does it need to go in the forward direction to get to equilibrium, or does it need to go in the reverse reaction to equilibrium? All right, let's write these two, looking at these. Kc would be, for this reaction, would be written as usual. Qc is the same exact formula. The difference is it's not at equilibrium. It's just sometime during if I stop at one point in the reaction, I were to freeze it if I could and measure their concentrations, but it's not yet at equilibrium. I could calculate Q. So if Q is less than K, I need to make Q bigger to get to K. To make it bigger, I need more in the numerator. That means that the reaction will be faster in the forward direction until the equilibrium is released. So to make Q larger, I need more concentration in numerator. So it's going to go forward to get there. If Q is greater than K, it's bigger than K, I need to make Q smaller. So I know that that means there needs to be more reactants. It's going to go in the reverse reaction. The reaction will be faster in the reverse reaction until the equilibrium is reached. And I can think about that as I need more reactant concentration in the denominator. If Q equals 0, the only way I can get 0 would be I have no products. And if I have no products, that means I have all reactions. It's definitely going to proceed in the forward direction. Has to. If Q ends up being infinity, the only way, right, if this was 0, if it was no reactants left, then the bottom would be 0, but you can't have a fraction with 0 in the bottom. If I take the limit of that fraction, it's infinity. So if Q equals infinity, that's implying that it's all products. Again, it can't be infinity, very likely, but it might be really, really large. So it's all products. Then the reaction is going to proceed in reverse. So if I know something about Q, or I'm told enough information to calculate the value of Q, and I know K, I can compare Q and K and to say, is this going to proceed in the forward direction or the reverse direction to reach equilibrium? So consider the reaction and its equilibrium constant. It gives me a reaction, it gives me its equilibrium constant. It tells me the reaction mixture. Notice it didn't say it's just a mixture. It doesn't say it's at equilibrium. The pressure of iodine is 0.114 atmospheres. The partial pressure of chlorine is 0.102 atmospheres. The partial pressure of ICl is 0.33355 atmospheres. Is the reaction at equilibrium? That's my first question. And if not, which way will it proceed? Now, to be at equilibrium, Q needs to be equal to K. So let's measure out what Q is. Let's measure out what K. It told me K is 81.9. So I know K. I'm going to calculate Q by looking at the reaction and writing the mass action, law of mass action. So the partial pressure of ICl squared divided by the partial pressure of iodine times the partial pressure of chlorine. Now I put in the values, 0.355 squared over 0.144 times 0.102, calculated out, it's 10.8. So Q, 10.8, is less than K, significantly less than K. That means it is not at equilibrium because they would have to be equal to be at equilibrium. Also, because Q is less than K, I need more product on the top to get this to be a bigger number. So it's going to proceed in the forward direction until equilibrium is reached. You can either memorize if Q is less than K, it will proceed in the forward direction. If Q is greater than K, it will proceed in the reverse direction. Or you can think about the numerator needing to get bigger, the denominator needing to get bigger, knowing that the numerator has products in it and the denominator has reactants in it, and think about which way it has to go. Either one of those will get you this answer. So a note about Q and ice table properties. So these are a little bit tricky problems. If Q is greater than K, the reaction will proceed in the reverse direction when making an ice table. So let's say I've figured that out. I know, okay, this is not at equilibrium and it has to proceed in the reverse direction. I can use an ice table, but it's going to be very confusing because if it's proceeding in the reverse direction, then I'm going to be subtracting from the products. The change would be a negative X for the product side, and it'd be positive X's on the reactant side because I'm going in reverse. And so I could do it, but it's going to look a little funny. I'll have negative X's for all the products and positive coefficient times X's for all the reactants. So I should first evaluate Q to solve for the equilibrium concentrations to see, okay, is this going in the forward or the reverse direction? So I compare Q to K. If it's going in the reverse direction, then I'm going to do some different things. Use the coefficients from the chemical equation as the factor in front of X in my change row of my ice table. It's going to be positive for substances on the side that the reaction is proceeding towards and negative on the reaction it's going from. So in other words, if Q is less than K, it proceeds in the forward direction. I'll have negative values for the reactants and positive values for the products in the change row. If Q is greater than K, I will have negative X values for the products in the change row and positive values in the reactant row. So when you see that, that can be pretty complicated and a little bit confusing. It all works out fine though. So then you would solve for X. You can try simplifying it and using the approximation answer for very large or very small equilibrium constants and test it, make sure it's good. Or you use a quadratic formula. So it doesn't change the solution part. It just then changes the setting up of the ice table.